All right, let's get right into it. We talk about temperature all the time, right? But have you ever really stopped to think about what makes a thermometer actually work? Well, it all boils down to this really simple but profound rule, the Zeroth Law of Thermodynamics. It's what created the universal language we use to talk about energy.
But first, we've got to get one thing straight. Your body is a terrible thermometer. I mean, just awful. We think we can feel how hot or cold something is, but what we're really feeling is how fast heat is moving, and that can be incredibly misleading.
Think about it like this. You've got a metal chair and a wooden chair sitting in the same room. The metal one feels way colder when you touch it, doesn't it? But in reality, a thermometer would tell you they're at the exact same temperature. The big difference is that metal is a fantastic conductor. It just yanks heat away from your hand super fast, and your brain reads that as cold. Wood, on the other hand, is an insulator, so it does that much more slowly.
So, this brings up a huge question. If our own experience is so subjective and unreliable, how on earth did we build a system to measure temperature that's objective and consistent? How do we put a real number on hot and cold that everyone, everywhere can agree on?
Well, the answer to that starts with a really core concept in physics, thermal equilibrium. It's this beautiful idea that energy is always trying to find a balance.
And you see this constantly. You leave a hot cup of coffee on your desk, and it slowly cools down, giving its heat to the air around it. A cold can of soda does the opposite. It pulls heat from the air until it warms up. That flow of energy, what we call heat, always goes one way, from the hotter thing to the colder thing.
And when does that energy transfer finally stop? It stops when both objects hit the exact same temperature. At that moment, there's no more net flow of energy. They've reached a state of perfect balance, and that's what we call thermal equilibrium. So here's the kicker. The only thing you need for thermal equilibrium is for the temperatures to be equal. That's it.
This idea of a balance is the key that unlocks our ability to measure temperature. And the rule that makes it all official is a giant in thermodynamics, even if it has a kind of funny name, the Zeroth Law.
Now, looking at this, it probably seems, well, obvious, right? It's just like that transitive property thing you learned in middle school math. If A equals C and B equals C, then A must equal B. It feels like common sense, but this obvious idea is the absolute bedrock of all temperature measurement.
So what's with that weird name? Well, by the time a guy named R.H. Fowler wrote this down in 1931, the first and second laws of thermodynamics were already a huge deal. They were famous. But scientists realized this new law was so basic, so fundamental, that it really should have come before the others. So instead of renumbering everything, they just, kind of cheekily, called it the Zeroth Law.
And here's where the magic happens. That third body, that object C, that's our thermometer. The Zeroth Law is literally the reason thermometers work. We can stick a thermometer in a cup of coffee, let them reach equilibrium, and get a reading. Then we can take that same thermometer over to a bowl of soup across the room and do it again. And just like that, we know if the coffee and the soup are the same temperature, even though they never came close to each other. It's like the thermometer is a universal translator, and temperature is the language they all speak. If the coffee can talk to the thermometer, and the soup can talk to the thermometer, then we know for a fact that the coffee and the soup could understand each other. Okay, so the Zeroth Law gives us the principle, the how of measurement. But we also need the vocabulary, right? We need to know how much. So let's talk about the scales we invented to create this common language of temperature.
So most of us are familiar with Celsius and Fahrenheit. These are what we call two-point scales. They're defined by two really reliable, reproducible things: the point where water freezes, the ice point, and the point where it boils, the steam point. But for serious science, we often need something even more fundamental.
And for that, we have absolute temperature scales. You've got Kelvin, which is used in the SI system, and Rankine in the English system. What makes them absolute is that they start at the lowest temperature that is theoretically possible, absolute zero. It's the point where all molecular motion would just stop. And because they start at this true universal zero, they are absolutely essential for any kind of thermodynamic calculation.
Now, converting between them is pretty simple math. But check out the last 2 points, because this is the really useful part. The size of 1 degree Celsius is exactly the same as 1 Kelvin. And the same goes for Fahrenheit and Rankine. This means if the temperature changes by 10 degrees Celsius, it also changes by 10 Kelvin. Super handy.
Okay, so we've got the law and we've got the scales. Let's wrap this all up and see why this stuff actually matters in the real world.
If you remember one thing, make it this. The zeroth law gives us the fundamental logic for how we can measure temperature, and the scales give us the language to say how much. And believe me, this isn't just for a physics class. This universal language is what lets engineers design everything from jet engines to power plants to the air conditioner in your house. It's all about precisely tracking and controlling the flow of energy.
So, I'll leave you with this thought to chew on. If this simple language of temperature has let us build our entire modern world, what happens as our understanding gets even deeper? As we get more fluent, what new conversations about energy in our future are we just now beginning to have?